Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be doing more topical past paper questions for A-level physics, for Cambridge A-level physics, and this is on the topic of ideal gases, questions 40 to 44. Now, as always, I'll leave a link in the description where you can go to the website and find these questions, and these questions are good practice for your upcoming exams. So attempt these questions, like I always say, attempt these questions and then come back to these videos if there's any point at which you get stuck or any question that's giving you a problem. So we're going to start as it's numbered with the Papa Cambridge questions. And again, these are not very clear, so I'll just write the question numbers down again. This is question 40, and this is 9702 is the subject code for Cambridge A-level physics. Winter 2019, so that's November-December exam 2019. Question paper for variant 1, and this is question 2 from that paper. Now, we are told in this question that the kinetic theory of gases is based on a number of assumptions about the molecules of a gas, and we are told to state the assumption that is related to the volume of the molecules of the gas. Now, specifically, we know that there are a few assumptions for the kinetic theory, but we are specifically asked for the assumption that's related to the volume. So I can only mention one possible assumption. I can't just remember and state all of them. So I have to be very careful. I need to know all of them because I'm writing an exam and I could be asked to name maybe a few of them. But in this case, I specifically want the one that talks about the volume. So what do we remember? Remember that the volume of all the molecules, when I add up the volume of every single molecule, it must be negligible compared with the volume of the container that's holding all these molecules. So compared with the volume of we can say the containing vessel is usually the accepted terminology, or you can say the volume occupied by the gas. So the region in which the gas is free to move around. But the volume of the molecules themselves, when you add up each individual molecule, that volume must be small, must be negligible compared to the volume of the containing vessel. And this makes sure that we have much more of a random Brownian motion and keeps the collisions in check and so on. So this is the only assumption related to the volume of the molecules of the gas. So you have to know all of them and be able to state a specific one if asked to state that specific one. If you state any of the others, you wouldn't score any marks there. Now the next question says an ideal gas occupies a volume of 2.4 times 10 to the minus 2 cubic meters at a pressure of 4.6 times 10 to the 5 pascals, and the temperature is 23 degrees Celsius, and we are asked to find the number of molecules in the gas. So our go-to equation in this topic is usually the ideal gas equation. And we know that PV is equal to nRT, or uppercase nKT, where R is the molar gas constant and K is the Boltzmann constant. Now we can use either one of these equations depending on whether we are given the number of moles or the number of molecules. In this case, we are asked to calculate the number of molecules, so I'm going to use the second equation. PV is equal to nKT. With a little bit of mathematics, N is pressure times volume over Boltzmann's constant times temperature. Thermodynamic temperature, that is. So pressure, and all of these values are given very nicely in correct units, so I don't have to do any conversions here. 4.6 times 10 to the 5 pascals times a volume 2.4 times 10 to the minus 2 cubic meters. Always make sure that your units are the correct SI units, not centimeters or millipascals, etc. Divided by K, again, Boltzmann's constant you can get from your data sheet, 1.38 times 10 to the minus 23. And the temperature, be careful, the temperature is in degrees Celsius, but we need it to be in Kelvin. So I take the value in degrees Celsius and I add 273. And I get a value in Kelvin. Remember, uppercase T is always the thermodynamic temperature. And what I get is 2.7 times 10 to the power 24. And so the number of molecules in the gas, I like to write my answer with the correct number of significant figures on the dotted line, is 2.7 times 10 to the power 24 molecules. And that seems about the right order of magnitude for this volume, this amount of gas, or this volume of gas. We are then told that each molecule has a diameter of approximately 3 times 10 to the minus 10 meters, and we want to estimate the total volume of the gas molecules alone. Now we know the mass, the volume of the containing vessel, but we want to know how much of that volume is contained specifically by these gas molecules. So I'm going to assume that each one of these molecules is spherical in nature. So the total volume is the number of molecules that I have times the volume for each molecule. I'll just call that V. And so this is 4/3 n pi r cubed. Where did I get this equation from? Because it's n times V, and the volume of a single molecule, since it's a sphere, you have to remember that the volume of a sphere is 4/3 pi r cubed, where r is the radius of the sphere. So this is 4/3 multiplied by 2.7 times 10 to the power 24, which is n, times pi, and the radius of each molecule is half the diameter, 1.5 times 10 to the minus 10 meters cubed. If I do this calculation, what I get is 3.817. You'd expect I get a small number, 3.817 times 10 to the minus 5 cubic meters, but I need my answer to be in one significant figure. So that's 4 times 10 to the minus 5 cubic meters. So I see that the volume that the gas molecules occupy is actually a lot less than the volume of the containing vessel. The volume of the containing vessel is 2.4 times 10 to the minus 2 cubic meters. So the gas molecules only occupy 10 to the minus 5 cubic meters. So 1,000 times less than the volume of the entire cylinder or entire container. And so only 1,000th of the volume of the container is being occupied by gas if we were to put the gas into a little corner. So what do we know here? Well, they ask us, by reference to your answer in B2, suggest why the assumption in A is justified. The assumption in A was that the volume of the molecules is negligible compared with the volume of the containing vessel. Is this justified? You're looking at our answer? Yes. Well, why is that justified? Because look at the value I've received. 4 times 10 to the minus 5, which I've calculated, is a lot less than that of the containing vessel, which is given as 2.4 times 10 to the minus 2. And this was cubic meters. And so what we can say here is that the volume of the molecules, and so therefore the volume of the molecules is a lot less than the volume of the container. Is much less than that of the container or containing vessel or whatever. And since there's a big difference, the ideal gas equation holds, and we can use the kinetic theory to explain the way the molecules behave. So the volume of the molecules is much less than that of the containing vessel or that of the container. And so our initial stage, so the whole question was sort of linked to each other, like they usually are in Cambridge. And we can see that from question A, calculating a volume and then showing that this actually makes sense, it actually holds true, that our assumption for kinetic theory should work because the volume of the molecules is a lot less than whatever's holding them. And so that was a 9-mark question. Not the longest question, but still required a little bit of work. Question 41 is the next question. And this comes from the winter exam of 2016. This is question paper 4, variant 2, and this is question 2 from that paper. We're told that the equation of state for an ideal gas of volume V at pressure P is PV equal to nRT, where R is the molar gas constant. And we are asked to state what is meant by the symbol N. Simply, the amount of substance, or more specifically, we know that little n, lowercase n, is the number of moles of that substance, whatever substance we are looking at. And then we are asked to state what is meant by the symbol T. Now you cannot simply say that T represents a temperature, because temperature can be measured in any units. But specifically, we can say that this is the absolute, or a word that means the same is the thermodynamic temperature. So remember, when we have uppercase T, we measure this in Kelvin. If I use theta, I usually then can measure in degrees Celsius. So uppercase T is the absolute or thermodynamic temperature. Always, when using temperature in an equation, use it in Kelvin. We are then told that an ideal gas is held in a container of volume 2.4 times 10 to the 3 cubic centimeters at a pressure of 4.9 times 10 to the 5 pascals with a temperature of 100 degrees Celsius, and we want to show that the number of molecules of the gas is 2.3 times 10 to the power 23. Now everything is fine. I know I can apply the ideal gas equation again. Uppercase N is PV over KT. The problem is that my pressure is in cubic centimeters. So I have to rely on my conversion skills. What I remember is 1 centimeter is 10 to the minus 2 meters. Great. But if I square the left-hand side, or rather cube the left-hand side, because I have a value of volume in cubic centimeters, I must cube the right-hand side. And so what I get 1 cubic centimeter to be is 10 to the minus 6 cubic meters. So a cubic centimeter is 10 to the minus 6 cubic meters. And so now I can put my values in. And so the pressure in pascals is fine, 4.9 times 10 to the 5 pascals. The volume is 2.4 times 10 to the power 3. And then I replace cubic centimeters with cubic meters, which means I must replace 1 by 10 to the minus 6. I multiply by 10 to the minus 6. And I divide by Boltzmann's constant, which I know again. Do not confuse the constants. If you are confused, just go to the data sheet, spend the extra time, but make sure you get it right. Multiplied by the temperature, which is 100 plus 273. Remember, it's thermodynamic temperature. And what I get is 2.285, or to two significant figures, 2.3 times 10 to the power 23 molecules, which is what we were asked to show. So indeed, we have the correct number of molecules of gas in the container. The only effort required there was to make sure we convert cubic centimeters to cubic meters quite easily. By now, this shouldn't be difficult to do, but if it does require practice, then I suggest making a specific practice session often and recurring so that you can practice how to convert units, because it's obviously going to come up often in A-level physics. The last question says, use data from B to estimate the mean distance between molecules in the gas. So what I'm going to do is I'm going to assume that my molecules of the gas are spherical, and I'm going to assume that my containing vessel, or rather, let's assume that that's my volume of all my molecules that my molecules occupy, and I want to know the mean distance between the molecules of the gas. So what I assume is that all these spherical molecules, try to make it look spherical, they all lined up so that the outer edges of the spheres, of each sphere touches the next sphere. They occupy a total volume V, and one specific molecule, since I'm not very creative, I'll say is V subscript 1 molecule. And the diameter of each molecule, remember these are spherical, the diameter of each molecule we'll call D. And so they're all identical spheres because all of the atoms are the same. So the volume of a single molecule, and we'll see what I'm doing here, the volume of a single molecule, so I'm assuming now that the atom occupies the space that is the size of a sphere. Obviously the atom might be smaller, but might occupy this spherical area, spherical volume. Is the total volume 2.4 times 10 to the power 3 divided by 2.3, and I'm working in centimeters. That's why I'm using 2.4 times 10 to the minus 3 as my volume, because my final answer wants the mean distance in centimeters. So there's no need to convert it to meters. Divided by 2.3 times 10 to the power 23. So the total volume divided by the number of molecules I have. And so that each molecule occupies this volume. And what I get is, I don't need to do this calculation now, but because this is quite complex, I'd rather have the mathematics done step by step. 1.043 times 10 to the minus 20 cubic meters. So each molecule on average occupies this area, this volume. Now the total volume, now this volume is 4/3 pi r cubed, or d over 2 cubed, which is half the diameter cubed. And I can simplify this and write this as 1 over 6 pi d cubed. So this volume we'll assume is spherical, the volume that's occupied by one molecule. And I should just remove the v so we don't confuse it. I'm using the same volume, and I'm assuming that the volume of each sphere is spherical. And so what I can do is, if I know the volume occupied by each sphere, I can estimate the mean distance from the center of one sphere to the center of another sphere, which is the diameter, radius plus radius. If I have two spheres that are touching each other, the mean separation between the centers of the two spheres will be the diameter, radius plus radius. And so what I get is the diameter, now I'm doing a little bit of mathematics here, is the cube root of 6 times the volume divided by pi. So I'm just taking this equation and rearranging it so that I can solve for the diameter. That's also the mean distance between consecutive atoms. And this is the cube root of 6 times the volume we calculated, 1.043 times 10 to the minus 20. Actually, this is cubic centimeters, not cubic meters. We can leave that in cubic centimeters because the cube root of cubic centimeters will just give me a centimeter. And I divide this by pi. And what I get is 2.71 times 10 to the minus 7 centimeters, which to two significant figures is 2.7 times 10 to the minus 7 centimeters. So that's the mean distance between atoms. That's the separation between the center of one atom and the next one. Again, on average, the atom might be smaller than this, but if I assume that they occupy the volume of a sphere, this is what the mean distance would be. You didn't have to use the volume of a sphere. You could simply use d cubed. You could have ignored the 1 over 6 pi or the 4/3 pi r cubed and just said d cubed. You could have assumed that each of these atoms is more of a box, and the separation is also d, and so the volume would be d cubed. You could use that, you'd get an answer that's different from what I have, but it will also be in the order of 10 to the minus 7, which is good enough. We want the order of magnitude to be correct. And so my order of magnitude is 10 to the minus 7, yours would also be 10 to the minus 7, but would be a different number in front of the 10 to the minus 7. And so that's the mean distance between atoms. So this is a kind of question that does come up often, but once you get the hang of it, you realize, hey, I simply need to take the entire volume divided by the number of molecules, and that's the volume occupied by a single molecule. If I know the volume, I can very easily determine the diameter or the radius or whatever it may be. So they may ask you to find the radius of one molecule, for example. And so that was a nice question, overall worth 8 marks. The last part, like we saw, could take a little bit of time, could take more time than the rest of the question to solve. The next question is question number 42, as numbered by Papa Cambridge, 9702. This is from the March 2021 exam. Question paper 4, variant 2, and question 2 from that paper. We are told in this question that a fixed mass of an ideal gas is at a temperature of 21 degrees Celsius. And the pressure of the gas is 2.3 times 10 to the 5 pascals. The volume is 3.5 times 10 to the minus 3 cubic meters. Calculate the number n of molecules in the gas. Again, this is straightforward. You can probably do this with your eyes closed. PV is nKT, which means, guess what? N is PV over KT. I've stopped actually trying to rearrange this equation because I've memorized different forms of this equation for doing it so many times. All of the values are given in the correct units besides the temperature, but that's not a problem. So I can just put the pressure in 2.3 times 10 to the 5 pascals times the volume, which is 3.5 times 10 to the minus 3 cubic meters, divided by Boltzmann's constant 1.38 times 10 to the minus 23, and the temperature is 21 plus 273. Again, you can do this in your head, but I suggest you don't. It's very easy to say that 17 plus 273 is 300, for example. It's a common mathematical mistake we can make, so it's best to just take out your calculator and do the temperature step by step. And what I get is 1.984 times 10 to the power 23 molecules. I don't need a unit of measurement because this is simply a number. To two significant figures specifically, this is 2 times 10 to the power 23. So again, nothing difficult, just make sure you're using the correct units when calculating number of molecules, temperature, pressure, volume, whatever. We're then told that the mass of one molecule of the gas is 40 U, 40 atomic mass units. We want to determine the root mean square speed of the gas molecules. And ominously, we have quite a large space here, which means significant working. Now you're going to have to go with your kinetic theory equation. PV is equal to 1 over 3 Nm and the mean square speed of the gas molecule. So PV is related to nKT, but also related to 1/3 nmc squared. This is a very important equation. But they specifically want the RMS speed. Now this equation doesn't have RMS speed in it. But what I know is root mean square is the root of the mean square. So it's the square root of c squared. And the square root of c squared is the square root. If I rearrange this equation, it becomes, actually let's do this. Let's write c squared as 3pv over nm. Remember, m here, little m is the mass of each individual molecule, which luckily for us is given. And uppercase N is the number of molecules. So the denominator here is just the total mass of the gas. So this is the square root of 3pv over nm, which is, now there's quite a few things that need to go into this equation. So there's a big square root sign, 3 times the pressure, which we know is 2.3 times 10 to the power 5 pascals, times the volume, 3.5 times 10 to the minus 3 cubic meters, divided by the number of molecules which we just calculated, 2 times 10 to the power 23 molecules. The mass of each individual molecule is 40 times U, whatever U is. But we know that U, the atomic mass unit, is 1.66 times 10 to the minus 27. Again, if you're unsure, be safe, go to the datasheet and pick up those values from there. And so what we get is a value of 426 meters per second, or to two significant figures, 430 meters per second. So if you are asked to find the root mean square speed or the mean square speed, always go to the kinetic theory equation. Write the kinetic theory equation down, because the other things are known, the pressure and volume and number of molecules. And when those things are known, that's the equation you would use to find the root mean square speed of the molecules. We're not totally done, however. The question has another part, which says the temperature of the gas is increased by 84 degrees Celsius. Calculate the value of the ratio of the new RMS speed to the original RMS speed. Now there is a relationship And I can't remember the actual equation, but I remember that there's a relationship between the mean square speed and the temperature. How do I know this? Because I know that average kinetic energy, or the molecules of a gas, remember there are trillions of molecules of gas, of a gas, and each of them have a different speed, but on average we can say what their kinetic energy is. And this is proportional to the temperature. In fact, kinetic energy gives us an indication of the temperature of a gas. Right? We define temperature as the average kinetic energy of a substance. And what we know is that the average kinetic energy is a half m times the average speed squared, the mean square speed of the molecules. Let me get that correct. The mean square speed of the molecules. Obviously, there's an n in here for the total number of molecules. To get the average speed for the entire gas. But what I can see is that it's proportional to c squared. So always remember that the mean square speed is proportional to temperature. The temperature goes up and the speed of the molecules go up as well. What this means is that the root mean square speed, which is the square root of the mean square speed, is proportional to the square root of temperature. I just square root both sides. So I'm going to write it with a superscript and a subscript. The new RMS speed over the old RMS speed, let's stick to convention. Since there's a proportionality, if I were to take two values and divide them, whatever constant of proportionality I had would disappear, and so this becomes the square root of the new temperature divided by the old temperature. Thankfully, I know both of these. I know both the temperatures. So the old temperature was 21, or the new temperature rather is 21 plus 273, but it's increased by another 84 degrees. So 21 plus the increase of 84 plus converting it to Kelvin. Now be very careful. Since temperature has an addition, has a relationship where we have to add to get the new unit, we can't simply ignore the 273 because then my ratio would be wrong. In any other case, in any other conversion, meters to feet, etc., I can drop out the whatever proportional constant is there to convert the units. But with temperature, I can't. And divided by the old temperature, 21 plus 273. And what I get is 1.134. Or to two significant figures, 1.1. Always make sure, even though it's a ratio, write it as a decimal number. We need to know how many significant figures there are, like we always need to do in science. So make sure that your ratio is always a decimal number. And so that question was worth 6 marks, but did require a little bit of working, especially when we needed to calculate the RMS speed and then this ratio. But you can see that we can do this ratio calculation. It's only 2 marks. We can do it in a relatively short amount of time. So get comfortable explaining relationships as proportionalities and then finding the ratio of something over something else. The proportionality disappears and becomes an equation, and then your calculation becomes much quicker and much easier. Now the next question is question 43, and this is from summer 2020. It's question paper 4, variant 2, and question number 2 from that paper. We're told that a square box of volume V contains n molecules of an ideal gas. Each molecule has a mass m. Using the kinetic theory of ideal gases, it can be shown that if all the molecules are moving with speed v at right angles to one face of the box, the pressure P exerted on the face of the box is given by PV is nmv squared, which leads to the formula P is 1/3 rho times the mean square speed, where the pressure is P for the ideal gas, but rho is the density of the gas, and c squared is the mean square speed of the molecules. And we want to explain how each of the terms that are shown below in equation 2 are derived from equation 1. So equation 1 becomes equation 2. So PV is equal to NMV squared, which means P becomes NM little v squared over big V, and the number of molecules and the mass of an individual molecule is the total mass. Total mass divided by total volume is density. Notice how my P is upright, but my rho is a bit more slanted. Don't confuse the two. As you can see, they're both in the same equation, so you have to make sure they look different. So the first one's easy to state where it comes from. Where does rho come from? Well, rho, like I said, is the total mass divided by the total volume. And please write the mathematics down. So what this means is I would write this as rho is equal to Nm over V. Total mass divided by the total volume. Next, where does 1/3 come from? This is a little bit more tricky. But remember, they said here that the molecules are moving in one dimension at right angles to the face of one box. One face of the box, rather. So I have to make sure that I account for the speeds of all the molecules. Now, if the molecules are moving at random, they should be moving in the x direction, the y direction, and the z direction. So how many dimensions of motion do I have? Well, there's 3 degrees of freedom. There's 3 dimensions over which these molecules can move. So I'm going to say that the molecules move in all 3 dimensions. And so if this equation is derived using only one, then I've missed out the other 2 dimensions. So the contribution that I'm given by the equation as I derived it above in any one direction is 1/3. So that's where the 1/3 comes from. The molecules move in 3 dimensions. Since the contribution is only in one direction, we have to add a term 1/3 in front of the equation. And lastly, V squared disappears to the mean square speed. And why is this? Because that's calculated for a single molecule. But all of the molecules do not have a single speed. They all have different speeds. So since the molecules have different speeds, we use the average of the speed squared. We use the average of the speed squared. Notice how I put speed squared with the hyphen, because we use the average of speed squared. And what I mean by this is this thing is the average of speed squared, and it's not equal to the average of speed squared. That's why I use the hyphen. It's the average of the squares of all the speeds, the mean square speed. Since the molecules have different speeds, we use the average of the speed squared. And so that's a lot of marks actually, but it's very important because essentially they're asking you to derive the equation. If you know how to derive the equation, then you'll know how to explain where each of these terms come from. So it's going to be 4 marks whether they ask you to derive the kinetic theory equation like they've done here, or they ask you to explain where the terms come from. And so you need to know that derivation. It's a long derivation, but it's an important one for A-level physics. Next, we are told that an ideal gas has volume, pressure, and temperature as shown. So volume 6 times 10 to the minus 3 cubic meters, pressure 3 times 10 to the 5 pascals, and temperature 17 degrees Celsius. The mass of the gas is 20.7 grams, and we are asked to calculate the mass of one molecule of the gas. Well, let's first see how many molecules we have, shall we? Because we have enough information here. N, again, in your sleep, is PV over KT, which is a pressure of 3 times 10 to the 5 pascals. Again, everything's given in correct units, so we're lucky. The volume is 6 times 10 to the minus 3 cubic meters, divided by the Boltzmann constant, 1.38 times 10 to the minus 23, And the temperature again must be converted to Kelvin. So 17 plus 273. This is the one I was telling you to look out for. In your mind, it's very easy to say that this is 300. You see the 7, you see the 3, and your brain does some of its own mathematics. But that's actually 290. So if I do this calculation, I get there to be 4.498 times 10 to the power 23 molecules. But I want the mass of one molecule of the gas. So what I do is, for specifically one molecule, and you can see where I'm going with this, I take the total mass of all the molecules and I divide it by the number of molecules. And so now I'll have the mass of one of the molecules. Assume that every molecule has the same mass as it should. So 20.7 grams. I'm using grams because my final answer is expected to be in grams as well. So I don't need to do any conversions. So 20.7 over 4.498 times 10 to the power 23, which gives me 4.6 times 10 to the minus 23 grams. Our final answer can be two significant figures, so I can write this as 4.6 times 10 to the minus 23. So a small number, but we'd expect one molecule of a gas, if measured in grams or kg, to be an extremely small number. And so that question was 8 marks, and the first part is essentially was the derivation of the kinetic theory equation, which again you need to know. Next is question 44. And this is from the March 2019 exam, question paper 4, variant 2, and question 2 from that exam. We are told that the pressure P of an ideal gas having density rho is given by 1/3 rho c squared. And we first are told to explain what is meant by an ideal gas. Now, we need to explain this thoroughly. We can even see this is worth 2 marks. So an ideal gas is any gas that obeys the equation of state. Or you can say that it obeys PV is proportional to T. So any gas that obeys the equation of state, PV is equal to nRT, or PV is proportional to T. But I have to state what symbols I'm using here. Now pressure is given, but I'm still going to have to state specifically that this obeys, the gas must obey this expression for all pressures P, volumes V. So I'm explaining each symbol that I'm using. I can't just state something with letters, but without explaining what the letters are. And temperatures T. And so an ideal gas is any gas that obeys the ideal gas equation, or the equation of state as it's also known, for all P, V, and T values. And this again you know from looking at previous questions or your textbook, etc. We then want to state what is meant by the symbol c squared. Now this is very important that you state what it means in simple English, in correct English, because it's very easy to say mean speed squared, or mean square speed, or mean whatever. But the correct way of saying it is the mean square speed of the molecules of the gas. Essentially, what you could also say is it is the average value of the square of the speeds of all of the molecules. So I take the square of the speeds for each individual molecule, I add them up, divide by the number of molecules, and that's what I get. So you can say the long way around, or you can simply say mean square speed. If you're comfortable saying mean square speed, that's fine. If you're not, say it's the average value of the squares of speeds of the molecules. Check my crash course out on the topic of ideal gases if you want some more clarity on the different types of statistical measures that we do in ideal gases. Now the next question says that a cylinder contains a fixed mass of gas at a temperature of 120 degrees Celsius. The gas has a volume of 6.8 times 10 to the minus 3 cubic meters and a pressure of 2.4 times 10 to the 5 pascals. If the gas is ideal, we want to show that the number of atoms is 3 times 10 to the power 23. Again, we probably are getting quite bored of this now, but it's best if we do get bored of things. It means we are mastering it. N is PV over KT. Pressure is given in the correct unit, so that's 2.4 times 10 to the 5 pascals. Volume is also given in the correct units, 6.8 times 10 to the minus 3. Now notice these questions from different exams all have the same orders of magnitude. The pressure is always 10 to the 5 pascals. Volume is 10 to the minus 2, 10 to the minus 3 cubic meters. Temperature is not more than 150 degrees Celsius. And so you can see a pattern emerging. And even the number of molecules, 10 to the power 23. So these can give you useful hints when calculating an answer and you're unsure what the order of magnitude should be. If I get that the mass of the sun, for example, is 10 kg, I immediately know that I have an order of magnitude problem, which means I have to recheck my calculation. So I divide by the Boltzmann constant and multiply that by the temperature, 120 plus 273, always convert your temperature to Kelvin. And guess what we get? 3 times 10 to the power 23 molecules. Usually a question that says show that something is equal to something wouldn't give you 3 marks, but more likely to get 2 marks. So this is a good question for you to make sure that you understand the ideal gas equation. We're then told that each atom of the gas, assumed to be a sphere, has a radius of 3.2 times 10 to the minus 11 meters. Use the answer in part 1 to estimate the actual volume occupied by the gas atoms. So here we calculated we have the volume of the cylinder, but now we want to know the volume occupied by the gas atoms. Remember, the total volume occupied by all of the atoms is the number of molecules that we have times the volume of each molecule. And we can use the idea that each molecule is spherical. Well, they told us it must be spherical, so we have to use the volume of a sphere, which is 4/3 pi r cubed. So that's 4/3, I'm just writing the n in front of the pi, times r cubed, because we are given the radius here. So this is 4/3 times the total number of molecules, 3 times 10 to the power 23. So basically we're taking the volume of one sphere, multiplying it by the number of spheres we have, and that's the total volume occupied by the gas. Multiplied by pi, times the radius, which is already in meters, 3.2 times 10 to the minus 11 meters cubed. What I get is 4.118 times 10 to the minus 8 cubic meters. Or to two significant figures, 4.1 times 10 to the minus 8 cubic meters. The answer is required in cubic meters. So we can see the gas actually occupies 10 to the minus 8 cubic meters, whereas the containing vessel is 10 to the minus 3 cubic meters. So 10 to the power 5 orders of magnitude less. And so again, obviously what we can see is the gas occupies a very little, a very small, negligible volume. You could expect that was going to be the next question. We are told rather, that one of the assumptions of the kinetic theory of gases is related to the volume of the atoms. We've stated this already in this video. State this assumption and explain whether your answer in 2 is consistent with this assumption. Okay, let's first state the assumption like we've done before. So the assumption said that the volume of the molecules is negligible in comparison to the volume of the containing vessel, or of the container. Does our answer from the previous question rather, does it confirm this assumption? Well, it does. 10 to the minus 8 cubic meters is a lot less than 10 to the minus 3 cubic meters. So what do I say? I need to say that my answer does confirm this, and it is consistent with this assumption. So 4.1 times 10 to the minus 8, and again, if your answer was in the same order of magnitude or larger, you'd know you made a mistake in the question, and you have to go back and check. So 4.1 times 10 to the minus 8 cubic meters is much less than the given volume, which was 6.8 times 10 to the minus 3 cubic meters. And so since there's a big difference, we can see that the volume occupied by the gas molecules is negligible. And so we can say, therefore, we have to conclude our thoughts. It is consistent with the assumption. And so you can see this is also a nice recurring type of question where they actually give you values to test whether the assumptions of the kinetic theory hold when you have a system that is behaving as an ideal gas, and the kinetic theory must hold. So this is the last question that we'll do for today. You can see many of these questions are quite repetitive and they're not quite difficult, but the next time I will maybe try to complete these questions and visit rather some of the topical past problems for other chapters to try and get as many as possible done before you guys write exams. But please, if this video really helped you, leave a like, comment, subscribe to the channel. Let me know if you have any suggestions or if you want me to keep going and if these are really helpful. But for me, Mr. K, that's all from now on Everything is Relative. See you again next time.